I'm super excited to talk to you today about the present and future of artificial intelligence. Whenever there's a buzzword and a complex subject matter, it's usually good to start with a definition. But it's actually a little tricky because the definition of artificial intelligence seems to be constantly moving. Whenever we solve a problem, we don't quite call it artificial intelligence anymore. It started with chess. A lot of smart researchers looked at other smart people and thought, well, we're really good at math and at logic and at playing complex games like chess. And so they started working on those kinds of problems, thinking that once they solve them, a lot of other things will just fall into place. But it didn't quite, because those were simulated environments that didn't have the same kind of noise that we have in the real world. So now researchers actually shifted largely from playing games, which is still an important area and can teach us some things, to things that we didn't used to consider as that much of high intelligence, just understanding spoken words. Seems relatively simple, we can all do it. But that was actually a really hard problem up until 2010, when deep learning changed it and was able to make much more progress on this. And now we don't call it AI anymore, it's just SIRI. It's just a speech recognition software. But that was a really hard problem that we weren't able to solve. And there's still some tricky issues in research in it. Another area that deep learning has made a huge amount of progress in recent years is computer vision, namely image classification. And this is the one time I'll try to explain a little bit to you what these kinds of models do and how they work. One of the most important ideas of recent years in AI is to have so-called end-to-end trainable models, where we take in raw input, for instance, the pixels of an image, and we want to predict a final output. For instance, is there a cat or a dog or a house or a clock in that image? And so as we put that raw input, the pixels, into these models, they keep trying to learn more and more complex representations. So as they start looking at the pixels, the first layer might only identify simple edges and blobs, which actually turns out to also have a good correlation to the early visual cortex in the human brain. But then as they go to the next layer, they combine these blobs and colors and edges to more complex textures. And then as they go further and deeper into these different layers, they'll identify object parts and then eventually combine those object parts to identify full objects. And that was really, really hard. And initially, people tried to manually identify, oh, if there's a cat, then maybe there are whiskers here, then this might increase the probability of a cat, and things like that. And now, this entire process, all these visualizations that you see here on this slide, they're all learned automatically just by giving it a lot of supervised data. Here's an image in its pixels. Here's the output that we care about. Now, we've actually been able to combine computer vision even with some language processing, and we can do quite amazing things in the last couple of years. Here you see a visualization of a recent paper of collaborators of mine, where we color code where the algorithm is paying attention to as it's trying to generate a description of an image. So you have a little girl sitting on a bench holding an umbrella, and you see that indeed when it's generating the word girl, it is looking at the girl. When it's generating the bench, it is focusing its attention on bench. Or a zebra standing next to a zebra in a dirt field. These are very factual descriptions. We're not going to get very interesting ones from them. But indeed, the first zebra it's focusing its attention on is the one in the foreground, and then to the next zebra, it's actually the one in the background, and you see that color-coded too. So computer vision algorithms have gotten a lot more sophisticated, and they're actually also telling us a little bit where they're paying attention to as they're trying to translate from visual data into text. It gets even further. We can also do so-called visual question answering. This is an interesting task where you basically, as training data, give it an image, a question, and an answer. And now you want to probe the algorithm. You can ask it lots of different kinds of questions about an image, and you see if it still gets it right or not. So the example here at the top, what color are the bananas, is a good one. Because if you didn't know the image, in 90% of the cases, you'd probably be correct just saying yellow without the image. But we have here the visualization also of where the algorithm is paying attention to as it's trying to answer this particular question. And it's actually focusing its attention on the brighter areas in that image and realizes those bananas are actually green and gives the correct answer. Another fun one, what is the pattern on the cat's fur on its tail? It actually focuses most of its attention, again, in that bright area on the cat's tail and correctly identifies this as striped. And another fun example, what is the boy holding? It's actually figuring out, based on the question, that you now need to focus your attention on the arm and the object below the arm, and correctly classifies this as surfboard. So those are some of the great applications that we're now able to do as long as we have enough training data about a certain domain. If you never show it a baseball image in its training time, it won't be able to answer any questions about baseball. There are actually even more powerful applications that we can now do with computer vision. One of the ones that I'm really excited about is in the medical field, particular oncology. This is a small startup, Athelas, that actually is automating blood cell counting. So you make a very small prick in your finger and you can count blood cells with the same kind of architecture as the one I showed you before. It's a convolutional neural network. And now that you make this so cheap, this used to cost a couple $100s to have people actually sit there and for each blood sample count how many red or white blood cells there are. Now that you can make this much cheaper, you can improve oncology care, you can identify infections and help patients with leukemia and so on. In general, I think radiology will also have a huge impact with AI. The problem with radiology is that we need a lot of training data, because unlike in a blood scan or a pathology scan, you're looking for 1,000 different things that could be wrong in a head CT scan. And it will take us a while before we could automate that entire process. So for a very long time, AI will work together with radiologists to improve that process. And in fact, we already know that we can identify certain things that can very quickly kill you. So for instance, a stroke or a so-called intracranial hemorrhage, brain bleeds, those we can identify very quickly. And then without knowing all the other things that might be wrong in a head CT scan, we can put those to the top of the queue in an emergency room setting. And that can already save lives. Now, we talked about computer vision and speech recognition as two successes of AI. There's actually still some areas that we're struggling with, and that is motor control. This is a DARPA Grand Challenge and a bunch of examples of some very expensive robots that are trying to walk around, open doors, turn levers, and things like that. And as you can see, we're still quite far away as a community. In fact, you could say that we're not even at the level of a bee yet when it comes to motor control. A bee is actually quite complex. It has 1 million neurons. It needs to identify a lot of different paths and so on, and we're not there yet. So that is a very active area of research. One of the most interesting manifestations of human intelligence, I think, is language. And in language, we're making a huge amount of progress right now, but there's still a lot of ways to go. So here's an example. I think we could do better now, but this is from 2011, when folks realized that whenever Anne Hathaway, famous actress, won a couple of Oscars, starred in a movie, the reviews came out, all of a sudden the stocks for the company Berkshire Hathaway go up a significant amount. So it was already clear in 2011 people were trying to use natural language processing for algorithmic trading, and in this case made the mistake of so-called entity disambiguation. They disambiguated Hathaway to the company instead of the actress, and then made pretty substantial monetary decisions. Where we have gotten better in NLP is actually on just text classification. In fact, here are a couple of examples of sentences that up until 2 years ago, pretty much every algorithm out there would have incorrectly classified. The first sentence is, in its ragged, cheap, and unassuming way, the movie works. So traditional algorithms would have said, well, it's ragged and cheap. So it's probably a negative sentence, because they haven't had the ability to capture the whole context. But now, and what you see here is we actually have 2 passes over that sentence. And in the second pass, the algorithm focuses much more on works, the movie actually working despite its flaws. So it correctly classified this as positive. And the second one is the opposite kind of example. The best way to hope for any chance of enjoying this film is by lowering your expectations. Again, a kind of example that is quite tricky, because algorithms in the past would just look at single words and it has best and hope and chance and enjoying, such a positive sentence, yet you can only get there if you already think the movie is pretty crappy. So those are examples that we can now do largely because of advances also, again, in deep learning. There's some active areas of research that we still work on, and one of them is text summarization. It's actually a really tricky problem. Pretty much every natural language processing and AI model that you've seen in the past only can generate at most a sentence coherently. When we tried as a community to generate longer sequences fully automatically in these end-to-end deep learning models, which usually didn't do very well. So this is a result from just a couple of months ago, where our group worked on summarization, and you see here at the bottom a longer document, and at the top you see the summary. And what's fascinating here is that the summarization algorithm learned to, some cases, copy and paste particular words, sometimes entire phrases, but sometimes it also picks and chooses which words to pick from which area of the longer document in order to generate the summary, and in many cases actually generates coherent, longer document summaries. And as the summary correctly says, to do this really well still remains an open research problem. One of the areas of NLP that I'm personally most excited about is question answering, because you can actually think of question answering as a task that encompasses pretty much every other NLP task. You can ask, what is the translation of the sentence into French? You can ask, what is the sentiment? You can ask, what is the summary? Right? In some ways, everything becomes a question answering problem if you have a really powerful question answering model. And so here, we worked on this really great data set that Stanford collected called the SQUAD, or Stanford Question Answering Data Set, that takes lots of Wikipedia articles and then asks crowd workers to collect questions, and then also different crowd workers to collect the answers. And the models that you now see that do well on this task are much more complex than the model I showed you in the beginning that had the same kind of layer, just learning more and more abstract representations. Language by itself also seems to require a lot of distributed computing in our brain that takes a lot of different parts and elements. Now, what makes me really excited and looking forward to this, to the next couple of years, is the number of people that are now entering the field. There's a lot of excitement in AI, and just in a class I co-taught with Chris Manning earlier this year, we had over 660 students at Stanford attending that class, even though it's a graduate level class, and there are hundreds of thousands of views on YouTube of pretty technical material. And that is very exciting, but as we see AI actually working, we have to acknowledge also that it's just a tool, and it will stay a tool for the foreseeable future. We don't really have to worry about Skynet or Terminator kinds of scenarios. But what is important is to understand that tools can be used in good ways and in bad ways. In some ways, AI is just like the internet or a hammer or cars. Right? You can use them as weapons, or you can use them to transport sick people. And it's important for us to acknowledge that. The tools are only as good as the people and the political systems that end up using them. In fact, if we use them well, I think AI, and especially AI-powered language capabilities, will allow us to improve our communication. Pretty sure we can eventually have a Babelfish in the next couple of years, where we talk in one language and we listen in another one coming live at the other end. We can improve access to information. Question answering is a great example for that. And in general, make work much more efficient. In fact, I think we'll be able to automate most of the basic human needs, like food. We can automate farming with computer vision and some simpler robotic control. We can build houses automatically, and so on. I think in the end, as human intelligence and productivity gets enhanced, I hope that will lead us to a future where we can focus on unique and creative tasks, and those kinds of tasks that require empathy, where we care for each other, and we can basically automate a lot of the boring drudgery that is out there. What's important to acknowledge is that AI is only as good as the training data that we give it. If your training data is sexist or racist, then the AI will pick those patterns up and, in some cases, repeat them or even amplify them. So as we're applying AI to more and more different areas in simple things like loan applications, but also more complex things like the financial system or the judicial system, and medical applications, and political advertisement, and so on. AI will eventually be in all of these areas. I think it's important that we think about regulations, or at least guidelines, to prevent the negative effects that could happen and that may have already been in our training data. And lastly, it's not just the data that might have biases, it's also the community itself. And the AI community right now is actually quite aware that we have a diversity issue, and that is something that we continue to work on. All right, thank you.